Hi, everyone. Welcome to our second webinar in our four-part webinar series on dynamic load understanding, the impact of structural loads on product development. We're really excited that you can join us today. And these are short webinars. These are a series of 4 short webinars, each 30 minutes apiece. So let's get right into it. So today's webinar is going to be on the winning formula, harnessing simulation and test for product development success. Okay, so this is a really key part of product development here. Our presenters today are me. I'm Tim Hunter. I'm the president and founder of Wolfstar Technologies. You can see my credentials here. I've got about 35 years experience doing simulation, test, and design. And my director of engineering is Cindy Murphy. She's also going to be a co-presenter today, and she's got 30 years of experience behind her too, and she's got a great, broad, and deep background in engineering. And just a little word of caution today. Cindy and I are going to be doing swapping screens midway through here, so there might be a slight little technical hiccup, but we'll make it work as best we can. Okay, so here we go. Let's get right into it. So, we all know there's a V diagram in product development. It's one of those standard tools that we see when we're doing engineering development. And this is great where you've got on the virtual side of things, you're going from the voice of the customer into system design, subsystem design, component design. And then when you want to prove out that design, you go into the physical testing world and you kind of go up the V, component, subsystem, system test, all the way up to product launch. So this is kind of the task for engineering here. And on the virtual side of things, that's great. It's cheap, it's fast, you can iterate very quickly here. And it's based on our knowledge, our previous knowledge, and our assumptions. And that knowledge can be flawed and our assumptions can be wrong, but it's the best we've got. Okay. So I mean, the downside is you're working on kind of this set of assumptions here. And then when we go into the physical test world, well, that's going to be expensive and slow. Okay. It's just the nature of doing testing, it's just what it is. But the upside, the huge upside here is it's based on the real world. So you're getting real world answers to your problems. So, even though physical testing is expensive and slow, it's a necessary part of product development and it's really key to our success. Okay. Even though it's expensive and slow, we still need to do it. Okay. So these are two things that we need to do, and we need to balance this out. And then really what we want to do is we want to try to get as much knowledge from the physical test world and bring it back into the virtual world when we're going through our design iterations. Because the design, because we get stuck in this design, build, test cycle in product development. And the whole idea is that we want to minimize that, right? Those design, build, test cycles are super expensive and super slow. And if we can reduce those by 1 or 2 or 50%, that's really going to save us a ton of money. Okay, so this is what we really want to do here. Okay, so let's take a look at this V diagram a little bit more. So the first part of this here, and this kind of be the format here. We got the V diagram here. We're looking at the top part of the V diagram here. We're really setting up the product requirements here. And if you recall back from our previous webinar, there was a whole section where we talked about early and clear requirements. And this is so important for doing your product development right. You need to make sure that you're collaborating, you're realistic, you're planning for iteration because things will happen, and you got to be clear, okay? And the key to making that all work is having the right collaborators. So you really want to make sure that you got marketing involved, you got sales involved, you got service involved. Service is super important here. You got the voice of the customer, and then make sure that you bring in manufacturing. Manufacturing has got to make your parts, so they've got to be a part of the upfront planning. And I know it's hard for manufacturing to do that because they're so busy with day-to-day stuff, but you've got to bring them in early on so they can influence the product. And by all means, you've got to bring in a senior technical expert from engineering who's got broad and deep knowledge on your product. So that person can be in these conversations and help make trade-offs in real time with these key stakeholders here. This is really super important. So getting this right is going to set you up for success. Okay, this is a really big part of the puzzle. And this is hard to do. It's hard to get all these people in the room at the same time. I understand that, but it's important. And then the next part, we're going to take a look at the next part of things here. And, the whole thing for simulation here in the system, subsystem, and component design is that you want to quickly iterate on configurations. You want to make trade-offs between competing requirements. You want to be able to cascade these requirements to subsystems and components. And you want to be able to use component and system models that can basically help drive the CAD layout and work with the design team on that. And you want to really have models now that you can actually use to guide your test specifications and draw and help design which tests you want to do. So this is kind of our overall goals for simulation. And if we kind of take a deeper dive here, if we look at system design, the whole idea for system design is that you want to have something where you can do hand calculations. You want this to be at the very high level, hand calculations. You want to have stick and beam models. You want to leverage parameter optimization, and you want to have these detailed system level models. Okay, so this is all about kind of making quick and easy calculations to kind of set overall parameters for your system. So I've got a little example here. So just to kind of go through a little textbook problem here. Let's say we want to do an engine isolation system, and our operating speed for this engine is 1800 to 8000 RPM. Okay, so this is what we want to do. We want to create an engine isolation system. And so we know an engine isolation system, well, it's going to be a spring mass system, right? The engine sitting on top of isolators, that's spring mass system, natural frequency is going to be square root K over M. And we want to provide 4 engine mounts here. Okay, great. So we look at 1800 RPM. Well, 1800 RPM is 30 hertz when you convert that into hertz. And then looking at your response diagram here, you want to be at 50% response, and that's going to say that you want to have your resonance of your mount system to be half of your driving frequency. So we want to be at 15 hertz for our mount system, and I'm just saying our mass of our motor here is 200 kilograms. And then just rearranging terms here, you get K is equal to omega squared M, and you do the math, and we figure out our spring stiffness for our 4 mounts is going to be 444,000 newtons per meter. Okay, so that's our stiffness for our mounts there. Great, we've got an initial design just from a sheet of paper with some very simple calculations here. Now let's set up a little FEA model. So here I've made a 9-node FEA model here. This, I've got 4 nodes to ground, I got 4 nodes on the engine, and then I've got the engine block up here, the lump mass for the engine, and we've designed this up. And let's just see if we got our calculations right. And look at this. This is the first natural frequency of this engine isolation system, and it's showing that it's at 15 hertz there. We did the math right. Now we've got a tool that we can very quickly and easily go in and say, hey, the engine mass change. We need to change the configuration of where the mounts are. Maybe we need to go from 4 mounts to 6 mounts, those types of things. We can work that out very quickly and easily. This model solves in like 30 seconds, okay? And then now you've got this basic model of the system, and now the whole idea is that you want to kind of say, okay, what are the operating loads? So saying, hey, my shaking force of the engine might look something like this. So I've got the vertical force of the engine and the horizontal forces of the engine. Here's a little cross plot of all that. So now I can excite that engine with these shaking forces, and now I can see how my whole assembly is moving. And look at the shaking forces going into the engine here. And now here's the forces being passed to the mounts, okay, to the frame. So the engine mounting system is doing its job. It's taking the forces out of the system. So your frame is not getting much shaking force. This is exactly what you wanted to do. And again, this model solves in about 45 seconds, okay? So you can go and iterate all day long on this. This is what you want. You want to have these quick, easy stick models where you can operate on these parameters, okay? And now that you've got these overall parameters, now you're going to go work with the CAD guys and start doing layout. So you'll do a layout for how the engine mounting system might want to look like. And now that you've got these shaking forces that coming in from the engine, so now these are the forces being passed from the engine mounts into the frame. Now you can use these forces to go through initial design iterations and play with configurations of mounting structures and things like that, and get the overall basic layout of this whole system, okay? So that's the important thing, is now that you've used the system design level stuff, you can now bring that into the subsystem design and play with configurations very quickly and easily here. And now that you've got that, now you want to start fleshing out the details of the components. And so the whole idea here is that we're going to basically go in and take the CAD models, take the shaking forces that we're putting into them, and now we can leverage things like topology optimization. So topology optimization is critical here because now you're going to get down to the minimal mass that your structure needs in order to withstand the loading that you're putting onto the system, okay? So this is just part of the critical ways of going through and optimizing and getting very robust structures. Okay, so now we've gone through the whole virtual side of things, and now we're going to switch over to the testing side of things. We're going to switch it over to Cindy here, and Cindy's going to take us into the whole testing side and show us how that works.
So we're going to talk about testing today. There's three basic components, three types of tests: a component test, a subassembly test, and a system test. The simplest test includes an individual part that has no connection to other parts or assemblies. It is a unit test. It has one component of the same design. It can include many test articles with the same design. The test is driven by loads and constraints that mimic real life as much as possible. And the constraints in our reactions are minor fixture components that imitate stiffness of mating parts. So that's loads and constraints. The test is driven in a lab by hydraulic or electrodynamic equipment. Setup can include various transducer options to control or monitor the test during operation, kind of like a strain gauge, an accelerometer, an LVDT. We can use those for setup and monitoring. And again, loads come from vehicle measurements or from load reconstruction method. With load reconstruction, both magnitude and direction are calculated. The main goal of the component test is to determine the defects. You would run the test long enough or load it enough to induce part failures. Because there are individual parts, the part design can be easily modified and new parts created and tested. You need to be careful that you aren't changing the overall setup or the stiffness of the part or the fixture, but you're able to quickly change designs. The component test should determine if the part meets the requirements such as material selection or design. And then the output of the test can then escalate to a subsystem test. That includes failure locations or loading. The next level of testing in the lab is sub-assembly testing. This is multiple parts assembled like the vehicle. Relatively compared to field testing, this is an inexpensive test compared to multiple axis full vehicle testing or field testing for a proving ground. Multi-axis testing is done in the lab. Subassembly testing parts and assembly should be design intent. Parts actual intended with a design that's intended by the engineer. And like the component test, loads and restraints should also mimic real life as much as possible. Load reconstruction is a significant way to represent real life loads. As with the component test, the main purpose is to identify failures and prevent failures. The advantage with a subsystem is to be able to test multiple parts that are included in the full vehicle. Another goal is to be able to study interaction between parts. Everything in the subassembly can be a candidate for evaluation. It could include fasteners that assess fatigue, fretting, ultimate failure. And then during subassembly testing, parts or interaction measurements can be taken to understand tolerances. Also, changes in part-to-part interaction for repeatability is a goal. Ultimately, the goal of this test is to assess the risk and determine reliability of the subsystem. It is often driven by a DFMEA, designed for manufacturing and assembly. This is a process that should be used when establishing design requirements. And ultimately, it should be done before the project starts. Another lab test is the system test. This is building on the subsystem and component tests. This is usually a road simulator. The full vehicle is replicated in this test using a multi-axis servo actuator setup. This would use 2, 4, 6, or 8 posts. Loading for testing is applied to the tire patch where the system meets the road. The system assembly is often controlled by a transducer or several transducers. Again, such as a strain gauge or an accelerometer. And like subsystem and component testing, load reconstruction is a significant way to represent real-life loads in simulation. Goals for the system tests are like those for component and subsystem tests, which is to identify failures and prevent failures. Ultimately, this is a high return on investment because it's less expensive than field testing and be done faster. We're minimizing design and assembly risk here and gaining confidence in the design. One more goal is to cascade requirements from simulation, tying it all together. Bringing everything together, functional testing can be component, subsystem, and system level testing. This is done in the lab. Acceptance testing is the final step in performance testing. This is a full vehicle test. The advantage we have is we can do usage configurations, loaded versus unloaded, effects of small stiffness part changes, things like that. We're ultimately gaining confidence in the design and eliminating risk of the design. We can prioritize risk based on product function. This strategy minimizes overall timing and cost. The goal here is to improve quality, function, and customer satisfaction. There's a theme here. Basic foundation to all of this is to fully understand loads, which is done properly with full vehicle data acquisition or load reconstruction methods.
All right. So Cindy, I think it's my turn here. So,
Yep.
So just did I share the wrong script? So thank you, Cindy, for that. So we kind of went through this whole V diagram here and how it's in this whole design, build, test cycle. And this is really kind of a Sisyphusian effort, right? This is really hard in product development to do. It's hard. It takes time. It takes money. This is something that we need to do. But the overall goal here is that we're trying to minimize the number of times that we're going through this cycle. We want to minimize that as much as possible. So we've got this huge task to do. It needs to be done, but we want to do it as few times as possible. And the way that we want to do that, and we've kind of talked about it a bit here today, is that we want to do knowledge capture from the physical world and bring it back into the virtual world in system, subsystem, component design. And we kind of touched upon that a little bit, talking about load reconstruction and other methods to do that here. And by the end of this series, I think you're going to see a very powerful set of techniques that we can do for doing that. But this is just kind of giving you the entryway of what we need to do, because we need to do virtual product development, but we need real world data to help us out with that. And there's got to be a bridge to help us do that. And I think we're going to show you some great tools in the next couple of webinars to do that. So sit tight. We're going to get to that point here, but this is the end of our webinar today. So thank you very much. And just, this is just where we want to be, right? We want to have our product development curve. This is coming from our last webinar. This is having our product development curve, and we want to move that forward in time, right? We want to do early and repeated learning on our product development cycle to the point where we can actually bring our launch dates forward, okay? Not miss the launch date, but bring it forward. And engineering can look like the hero to the organization, okay? Because we're the smartest guys in the building, so we should be the heroes, right? So just thank you very much for taking the time to join us today. We really like talking to you and showing you these great techniques. Our contact information is up here. Our email addresses and there's mine on the top left, and then Cindy's is up there, and then Susie Ralston is our business development manager. We'd all be very happy to connect with you, so please reach out to us. Our website is right here, and the QR code is for our website. And please come back and join us again for our next webinar in the series. It's going to be on November 8th, and it's going to be Sculpting Success, Achieving Seamless Proper Product Representation with FEM Simulation. So this will be doing a bit of a deep dive into FEM techniques for doing product representation of product, okay? So this will be a little bit more heavy on the simulation side of things, but this is important to do, okay? So thank you very much. I'm very glad you could all join us today, and we will give you recordings of this webinar today. We'll follow up and send you a link for the recording, okay? So thank you very much, everyone. It's been great talking to you this morning. Take care. Bye-bye.